I'm currently the CEO of Allied Titanium, and Allied Titanium was spun out of a marine mechanical company that I founded in 1988. And by 2002, let me pull up my notes so I don't get these numbers wrong. By 2002, 20% of our revenue was coming from polished 316 stainless steel. And these were chain plates, tangs, railings, steering arms, all kinds of parts. And at the time, I believed that if stainless steel, particularly 316L, was kept polished, that it was immune to corrosion. Well, in February of 2002, a bunch of boaters were standing around the docks in front of a vintage 1970s Columbia 50, and it had just had a brand new head stay and roller furling system put on it. And the roller furling system gave way and the mast came crashing down, of course, destroyed the sails, destroyed the roller furling, but fortunately didn't hit anybody. And the owner started investigating what had happened. And on the deck of the boat, he found crumbled pieces of a Crevice pin, excuse me. And so I didn't know this guy, and he launched an investigation. And according to the information I got from him later, he said that this pin had been purchased from a chandlery. He was under the impression that it was brand new, and that this crevice corrosion had happened while it was sitting on the shelf, supposedly. And he did a bunch more investigation and found that this could happen within 3 years. Well, I paid attention to what he had to say, but of course, it seemed a little bit far-fetched to me. I believe that more likely he, was using a used Crevice pin. So let me see if I can get the PowerPoint going here. Hold on.
Do you need technical input?
Yeah, I've got to get this thing to show part screen here. Hold on.
So have you shared your screen? If you click the share the screen button.
Yeah. Normally I don't see the share the screen like we normally see there. It's for this. There it is. I got it.
Got it? Yeah. We've got you. That's coming in.
Okay. Let's see if this. Now, can you see the PowerPoint?
Spot on, Chris. Spot on.
Okay. So I'm actually going to go to the slide. So these are bolts that were removed from a chain plate that we changed on a customer's boat. Okay. And so after the incident with the the roller furling coming down in December. Does this work? Can you guys see this? You should be looking at an accident in Hawaii.
Yep, we've got that.
Okay. Can you read it clearly? This is the area I want you to focus on.
Yeah, it's good for me, Chris. Yeah.
Okay. So this was in December of 2006, and a tourist boat off of Waikiki had an accident, where maybe some of you know about this, where this kid was killed when the mast came down due to corrosion. Okay. Unless I got to draw this down and then go to the next one here. And I'm not going to go through the whole thing, but suffice to say that a bunch of my friends were there when they brought his body off the boat, and it sent shockwaves through our industry. Fortunately, this was not my customer, thank God. 3 months later, in March of 2007, another guy gets killed when a mast comes down off of a tourist boat operating off of Lahaina, Maui. The Coast Guard launched an investigation, which I think I have right here. If I drag this over, can you guys see this?
Yeah, we're seeing that.
Okay. So as you can see, it took quite a while for this investigation to occur. Suffice to say that they went around and they looked at a lot of the tourist boats and a lot of the other problems that they were having, and they found all sorts of problems with the stainless steel. So short time later, one of my customers had the boat T-boned, and the stainless steel was Crevice from the inside. When we went to cut it open, it looked beautiful on the outside, but it was Crevice and shot from the inside. So we stopped manufacturing or doing any stainless steel work whatsoever. Now, I wanted to put up this definition of performance. And I'm going to change the subject here quite a bit, because mankind moves forward in technology in a way that the technical achievements tend to change our cultures and result in those that adopt the best performance related techniques to become dominant in the world, right?
Oh, shit.
So we went through the Stone Age, the Bronze Age, the Iron Age, and so forth. Obviously, the Stone Age tribes were obliterated by the Bronze Age tribes. The Bronze Age tribes got obliterated by the Iron Age tribes and so on. And we moved into the Steel Age. And here's basically the whole history of the adoption of the different technologies. And stainless steel, of course, was fairly late, 1913 thereabouts, right? Now we move into the titanium age. Now, what happened is that we started looking for a different material, a metal, to work on our customers' boats, because we had a bunch of top tier customers, and of course they wanted the bright shiny stainless steel. And we investigated going back to bronze for our marine work, but the problem is bronze is weaker than stainless steel, and so the insurance companies were requiring that we would have to get marine engineers to certify all the changes in the parts from stainless steel to bronze, which was not financially practical and was definitely a no-go with regard to the customers. Now, I didn't know anything about titanium at the time. And so in the course of trying to find other metals that would work, I investigated titanium. So here's a timeline for titanium. And of course, it was discovered a long time ago, but it was never adopted. 1916, first commercial application of titanium dioxide. 1932, William Kroll figures out how to do the Kroll process. 1940, he comes to America and he figures out how to do it in mass. 1948, DuPont company starts to produce it. 1960s, military applications and so forth. Today, in the aerospace industry, there are many people that know about titanium and use it all the time. But outside the aerospace industry, traditionally, few people and workers work with titanium. Now, there's some exceptions to that. The exceptions are in Russia and in China. So some of you may have traveled on this train. If I can get this to come up by dragging it over. This is a maglev train. Obviously, it's using magnetic levitation. There's a lot of titanium in it. in the magnets, etc. It's all over the place. It's extremely fast, extremely quiet. It's awesome technology if you've ever ridden it. The bullet train. The chain, this is more of a traditional chain, but they are using high technology all over through this thing. The Dreamliner. On that.
This is our home.
So this one, here's the Wikipedia for the Dreamliner. And one of the interesting things about this was when they first came out with this plane, it was too heavy. And so they had to reduce the weight. And of course, they turned to titanium for this. If I can get it. So. It was 5,000 pounds heavier. And so they basically took a bunch of steel parts, turned them into titanium to reduce the weight. Here's a titanium market report. Aerospace has traditionally dominated titanium, but truth is the industrial use of titanium has now outpaced aerospace. Looking to the future, here's another interesting thing, shows how many tons of titanium are in these planes. The Airbus A380, 77 tons. They're using it a lot. And of course, people are using this all over the place in the aerospace industry. 3D body printing.
This titanium jaw.
This was printed and put into a woman whose jaw had deteriorated due to osteo problems. So what is titanium? Most of you probably know by weight, titanium is the strongest metal in the known universe. Lightweight reduces the burden for man and machine. Corrosion freedom stops the insanity of continual replacement. Biocompatibility stops the poisoning of those working with titanium. Here's a little bit of the history, which I covered. These are the different processes. So I'm not going to go through these, but I do want to open them up so you guys can grab the links if you're interested in this. These are done by Oak Ridge. And so if you just go to YouTube and you search on titanium curl method, it'll go through how it's made. The Armstrong process. Same thing, US Department of Energy. Search titanium Armstrong method, you can get that. Metal cyst.
The FFC Cambridge process begins when a metal oxide has
Completely different process. Metal cyst, FC process. Search that on YouTube and you'll find that. So the benefits, osteointegration, it's compatible with all life, and this is why they're using it for body parts. Strength, 3.5 times greater yield strength for TI6Al4V than stainless steel. 44% lighter than stainless steel, corrosion free. Why isn't titanium being used for everything? This is a core question. Most people believe it's rare. Well, it's not. 4th most abundant metallic mineral, 9th most abundant element in the Earth's crust. It makes it up 0.66% of the Earth's crust. Now, here's an interesting thing. Pretty much everything that we eat and that is white has titanium dioxide in it, TiO2. They use for paint, sunscreen, food, whatever. Chances are you're eating this every single day. Is it expensive? Well, it's expensive if you don't know what you're doing. So I'm going to stop the PowerPoint here for a minute. So what it is that titanium is very plentiful, but most people, it's mysterious. They don't know a lot about it. They don't work with it. The exception is in Russia and China. Russia, they have made a big push for many, many years to work with titanium. They built awesome submarines that outperform anything the Americans have ever made, and so on and so forth. China is smelting 100,000 metric tons of titanium per year. Most of that titanium is going into their military and into their economy. They do export a little bit of it, but not a lot compared to how much they make. The reason why they're doing this is because it's a superior material, and so they're using it everywhere. They have a program where they take farmers out of the fields, they put them through 6 months of vocational school to teach them about titanium that's paid by the central government. Then another 6 months, they go into a titanium products factory or a mill, and that's paid by the provincial government, the local government. And then at the end of that period of time, so they've got a year of training so far, at the end of that period of time, they are brought in as an apprentice by the factory where they were paid, where the factory got them to work for 6 months for free, basically. And then they work as an apprentice, and at the end of that period of time, they're a full-fledged titanium worker. So they are moving forward very, very, very rapidly with this. Now, I'm going to just tell you a couple of things that happened. Basically, my boat, I have a 55-foot Pearson, and my boat had crevice corrosion in the clevis pins. And when I examined the broken chunks of the clevis pins that this customer, where his roller floating came down, I looked at the outside, and the clevis pins had somewhat of a little bit of a bronzish color to them. When I looked at my boat, I saw the same color. So after going every which way about every metal I could possibly think of, basically I decided to put in aerospace grade 5 titanium clevis pins. So I went and started trying to find somebody to manufacture these clevis pins. A lot of them were 3/4 inch, and so they weren't easy to find. I found grade 2 clevis pins, but I did not find grade 5 clevis pins. Grade 2 titanium is commercially pure titanium. Grade 5, of course, is the aerospace grade, 6% aluminum, 4% vanadium. Long story short, the cost of these pins was going to be around $2,500 for 50 pins, and it was going to take me 3 months to have them made. I got an email from a guy that turned out to be from China, and he offered to make the same pins for $236 out of aerospace grade titanium, which was a bit of a shocker, to put it mildly. And so one of my customers was Jack Chrysler from the Chrysler Corporation. And when he looked at it, and I actually placed the order, got the pins, and they were beautifully machined, gorgeous pins. He basically said, Chris, you got a business opportunity here. What you need to do is fly to China, get a manufacturing agreement with these guys for exclusive rights to the world, and go into business. So basically, that's what I did. Now, the first time I took my trip to China, and I went into this factory, there were titanium bars scattered all over the floor of this factory, on the floor, being ground into the concrete. So I said to the factory owner, I said, well, shouldn't somebody pick these up? And he looked at me and said, you Americans think titanium is so expensive. And he walked off. About a half an hour later, I'm watching this girl making bone screws on this, what looked like a vintage 1940s machine. And she's making a bone screw every 30 seconds on this machine with using a ratchet turret lathe. And she was turning the spindle at very high speeds, much higher than I would thought would be realistic. So I said to the factory owner, isn't she turning that spindle a little bit fast? He looked at me and he said, And that's why you Americans aren't going to be able to make titanium cost effectively. And he walked off. Well, at that point, I realized that I had a lot to learn. And I basically decided to take all my preconceptions, everything I thought I knew about titanium, and throw it out the window and start paying attention to these guys. So what I discovered with, number one, it wasn't hard to work with. It wasn't expensive. And so what I'm going to do here is I'm going to go to a video of Jack Chrysler. He was my mentor for the first, 5 years or so of Allied Titanium. I'm not going to play the whole thing. You guys can look this up on YouTube.
I'm
as
Jack
well.
Chrysler. You may know me best because my grandfather founded Chrysler.
I got to share this, right?
I'm Jack Chrysler. You may know me best because my grandfather founded Chrysler Corporation, the automobile company.
Can you see this okay now?
That's good.
What you may not know is that I founded Chrysler Aviation in 1977, which means I've been working with titanium for many years. This is my vessel, Valhalla. We're leaving for the island of Molokai, Hawaii tomorrow. There's not 1 ounce of titanium on this boat. She's loaded with stainless steel, shiny stainless steel, as you can see. Pretty, isn't it? But the problem is it costs me about $3,000 a year to keep this stainless steel polished the way it is. I'm sure you realize that stainless steel is primarily made out of iron, and iron rusts away. So if I don't polish Valhalla stainless, it rusts. What you probably don't know is that stainless crevice corrodes from the inside out, even when polished. Those tangs of crevice bin have crevice corrosion in them. When it fails, Valhalla's mast comes down.
I talked about the bronzish look of a stainless steel. That's what it looks like.
What are those parts? Shiny on the outside, but looks like dirt on the inside. This is a dolphin striker toggle. Doesn't look good. These tangs were holding up somebody else's mast. Looks like their mast came down. What this means is that every piece of stainless steel on Valhalla is on a time clock, corroding from the inside out. It will all have to be replaced eventually. Enough of that. We're leaving for the northern coast of Molokai, one of the most beautiful places in the world. In the aviation industry, we've been reaping the benefits of titanium for years. So one has to ask, in the marine industry, why aren't we seeing titanium all over the place in pleasure boats and ships? There are several reasons for this. The first is a complete lack of understanding concerning titanium. Titanium has 3 benefits over all other structural metals. First, 6-4 titanium is 3.5 times stronger than 316 stainless steel. 3.5 times stronger. This means if you make a part out of titanium and only use half as much metal, that part is still stronger than one made of twice as much stainless steel. Did you get that? The second benefit is that it is lighter, 44% lighter than stainless steel. With the rising cost of fuel, reduction in weight becomes all the more critical. Where's that bolt? Thank you. You can't feel this, but it's weird. If you're used to the weight of steel, the reduction in weight of titanium just doesn't seem possible. The third big benefit of titanium is that it is immune from rust and crevice corrosion, which means that a part of titanium is a part that will last virtually forever, even in salt water. So there you have it. It's lighter than stainless steel, it's stronger than stainless steel, and it's immune to all environmental corrosion. Hey guys, we got to prepare to go into Alawite Harbor right now. Every one of these vessels at the Alawite Marina is suffering from stainless steel crevice corrosion. In other words, the metal is corroding from the inside out. I'm going to show you some pictures of what this looks like. For you boat owners, especially those of you running tourist operations who have had some serious incidents lately, when you see significant rust running down a stainless steel part or weeping from a crack, it means you've got crevice corrosion inside your metal. This is what I'm talking about. Remember, stainless steel is primarily made out of iron, and iron rusts. The chrome in the stainless keeps the metal looking good on the outside, but what's going on the inside is what counts. In this photo, the iron is corroding internally, creating pressure until the metal cracks. That picture was taken in this harbor, and that part holds a lifeline to keep people from falling overboard. When you consider the benefits, comparable cost of stainless steel, 44% lighter, 3.5 times stronger, immunity to crevice corrosion, why wouldn't everybody be switching to titanium? One of the reasons has been lack of availability. Allied titanium is changing that.
So basically, we spun alloy titanium out of this marine mechanical company that I own. And we thought that it was going to be an easy business. So we started manufacturing marine parts, started making chain plates, tangs, you know, everything imaginable that for the structural parts. And our customers were happy. But we went to the boat yards, and one particular boat yard is in Kona, Hawaii, on the Big Island. And we were going to be manufacturing trailer spindles for all these trailers. And of course, the workers hated changing out corroded trailer spindles for all the boats back into the salt water. And so they were very happy with the idea of making a trailer spindle that would never have to be replaced. The manager thought, oh my God, this is going to be great. We can charge more for the spindles. We won't have to deal with all the hassle of the labor. Once we change it, it'll be done. It'll be a great thing. So we started the project, and along comes the owner of the boatyard. And he looks at it and he said, so let me get this straight. These don't corrode? And the manager of the boatyard and all the workers said, nope, they don't corrode. It's a permanent replacement. They're stronger. It's going to be great. And the owner looked at him and they said, are you crazy? Boat trailer spindles are 30% of our revenue. Get this stuff out of the yard. And boy, quick as that was the end of that. Now, what we found is that about 50% of the people that work in the marine industry are dependent, their jobs, their careers are dependent upon the idea of the continual replacement. So if you come up with a material or a part that doesn't ever have to be replaced, depending on the type of person you are, you may be adverse to the idea of doing that. So for example, we've had customers where the entire rigging was spec'd out to be changed out to titanium, and along comes the rigger. He takes one look at this and he says, we are not doing this. And he switched everything back to stainless steel. About 50% of the people, they embrace titanium because they believe it's the right thing to do. And I'm talking about the actual marine workers. And so with those people, we worked with them and we developed all these marine parts. A lot of them were standard parts, clevis pins, dolphin striker toggles, etc. When we went to actually start mass producing the stuff and putting it on the boats, the customers, of course, wanted the parts installed with titanium fasteners. Well, we weren't a titanium fastener company. We were a marine part company. So we made titanium marine parts. So we would send them out to other vendors and other manufacturers to make these fasteners. And of course, these fasteners came back in many cases costing more than the part. They were astronomically expensive. And this put a huge crimp in any hope of our business being successful. So we backed up and we realized that we were going to have to become a fastener company because the cost of the fasteners was so high that there was no way that we were going to be able to ever, spin this marine part business up to the point where it was practical. So for the next 5 years, we poured millions of dollars into drafting and design because another thing happened. We discovered that there wasn't any standardization for titanium fasteners. So we have ANSI standards for stainless, we have ANSI standards for bronze, we have ANSI standards and ASME standards for steel. There aren't any for titanium, which boggled our minds that this would be a material that would be completely left out of the standards program, so to speak. So that means we basically had to come up with our own designs. And what we did is we relied on our customers for the designs. Some things like a regular bolt, we made some changes to the bolt, increased the underhead radius under the head between the shank and the bolt head and so on and so forth. But sometimes we had to do serious engineering and try to figure out, okay, what's the best way to make this and what's the best way to make this thing gonna work. Now today we have over 100,000 titanium products for sale. And we worked really, really hard to get our prices comparable to stainless steel. Now, truthfully, they're not comparable with stainless steel, even though Jack said it was. There are some parts that are comparable in price to stainless steel, but most of them are 50% to 100% or even more than the stainless steel parts. But because we worked so hard to get our costs down through, database systems, computers, manufacturing methods, and so on and so forth. And of course, manufacturing in different countries. Our cost in relationship to the other competitors working in titanium ended up being significantly lower, and our business in the industrial markets took off. So today, Allied Titanium is primarily known for manufacturing industrial parts. We do quite a bit of aerospace parts as well, and our parts are in satellites orbiting the Earth. They're down at the deepest parts of the ocean and so on and so forth. The reality is that marine industry is probably only about 10% of our business right now. Now, we still believe that the marine industry is by far the biggest marketplace for titanium in the world. For the simple reason that the amount of money that's being spent on corrosion abatement is astronomical. So I will get calls from people who, for example, they're starting to run ships around through over the North Pole, and they're having a hell of a time with corrosion. And so some people are saying, well, let's start building the ships out of titanium superstructures because we don't have to paint them. We don't have to deal with the fact of those huge temperature variations where the paint is popping off and so on and so forth. We also get people contacting us, wanting us to build boats, titanium boats, high-tech designs. But most of these designs, in fact, all of these designs that have come our way have been based upon aluminum. And the problem is you've got to do re-engineering. It's not a situation where you can just swap out one metal for the other. There has to be re-engineering done. And that's expensive and time consuming. And so moral of the story is we haven't gotten involved in that. Now, one of the things that's driving these people to contact us and want us to start building boats out of titanium is because the United States military has had it. Basically, Russia and China are going full blast into the marine industry with titanium in their ships and submarines, etc. Americans are not. So the people and companies that are promoting and bringing these high-tech designs to the military out of aluminum are being turned down by the military and being told, go back and develop something out of titanium and we'll talk to you. Now there is some movement in the marine industry. So if you go back to Jordan Loser's death, it turns out that one of the large catamaran operators off of Waikiki has hired Jim Betts in Anacortes, Washington, to build a all titanium catamaran. It's almost done. Some of you may know about this, I don't know. It's an interesting project. The problem he's running into is the same problem everybody runs into, is design issues and engineering issues and manufacturing issues. So just let me give you a simple example. We weld titanium with TIG, wire feed TIG. And of course, Jim Betts' workers are used to working with MIG. They're not used to working with TIG. So now you're talking about having to train your workers how to use a TIG, wire feed TIG versus MIG. Well, what Jim did is he got a hold of, I believe it was Miller, and had them design a welder, a MIG welder that uses titanium. And so he's discovered through trial and error that for corner joints, 90-degree joints, etc., he can use MIG. But when it comes to flat plate connection, where he's putting two plates together like this, he's got to use TIG. But that's an example of some of the innovation that's happening in terms of with him in order to get this boat out the door. So there is movement happening in the marine market. Let me get this back up. Hold on a second. I'm going to share again.
That's better. You know, there's more titanium in the earth than all the nickel, copper, chromium, lead, tin, and zinc put together. Titanium is the fourth most abundant metal after iron, aluminum, and magnesium. When titanium became available after World War II, many thought it would become as commonplace as aluminum. This didn't happen because it was too expensive and mostly due to the high cost of refining. Now this is changing as new smelting technologies come online. What's going on now is the cost of stainless steel has been going up, while the price of titanium has been coming down. This is creating a revolution in metal, and allied titanium is on the forefront of this revolution.
Share again, how do I? So basically, I want to leave enough time here for questions. So go ahead.
Right, who wants to open up some questions for Chris?
You guys put it in the chat, I presume, right?
So Lee says, enjoying this greatly. Can you touch on galvanic issues when, oh, hang on, let's just open this up. When used in such applications as chain plates against an aluminum mast?
Okay, that's a good question. So if you, those of you that work in with stainless steel and aluminum, you probably have seen many times where the stainless steel and aluminum start to bubble, and basically what happens is it gets just completely seized up. You can't even get it apart. Now, grade 5 titanium is 6% aluminum and 4% vanadium. When you, next time you, hopefully someday you'll be able to, but next time you get on a jet plane, when you walk down the jetway, the doors open, and to the left of the door, to your left, is going to be the hinge. And you're going to see some bolts there, actually flathead screws. Those are titanium, grade 5 titanium. And you'll notice that they're not getting any crevice corrosion there. Obviously no crevice corrosion, no galvanic corrosion here. So what we do is we use Tef gel in between, but in all of our installations we've done so far, we have not seen the problem of the galvanic corrosion at that joint with grade 5 titanium. I can't speak for grade 2 titanium because the marine parts that we make are almost universally made out of grade 5 titanium. I believe that there's something going on there with compatibility between the aluminum and the grade 5 titanium, because the grade 5 titanium actually has aluminum in it, but I can't tell you all the chemical, what's going on there. Titanium is at the top of the galvanic series, as most of you probably know. And so if you're working in solid water with aluminum or whatever, and you've got electrical currents going through, then the less noble metals are going to be giving it up to titanium. Next question here is, where do you source the raw material? Okay, there are 4 countries that are smelting titanium. And so those countries are Russia, China, United States, and Japan. There's a pilot plant, metal sieves pilot plant in Britain as well. Some of you may know that. They're not producing real large amounts yet. I have high hopes for it, but the reality is that most of the titanium in the world is being produced by the Kroll process. Now, if you go and you look at the videos that Oak Ridge made, you'll see that the Kroll process is just nightmarishly complicated and expensive. This is one of the things that's keeping the cost of titanium high. The Armstrong process uses a completely different methodology. The problem with the Armstrong process, and we do have a plant here in America, in Illinois, that produces titanium by the Armstrong process. That process results in the titanium having a high oxygen content. And for many applications, there's just too much oxygen in the titanium to make it have the properties that you would normally want for aerospace and so on and so forth. So to answer the question, these 4 countries are smelting the titanium. Unfortunately, TIMAT just shut down their smelter in America. And so in terms of any mass production of smelting in America, it's over right now. So one of the things we're looking at is trying to work with the National Science Foundation to try to come up with a pilot plan to be able to start using some of the newer technologies with regard to smelting titanium. This is strictly my personal opinion, but Russia has the oldest smelters, and those smelters tend to produce titanium that has a little bit higher iron content than is normally desirable. They do produce a lot of titanium that meets the specification for grade 5, so I can't really say that's a bad thing. Japan does a really good job with titanium, but their costs are considerably higher, so it tends to be more expensive. Most of the titanium imported into America is coming from Japan. China is producing the most titanium by far, and their titanium is coming from new smelters, and it's very, very good quality. When we founded Allied Titanium in 2007, China had 25 titanium smelters under construction. As far as I know, all those smelters are all online now, and China's just pouring out the titanium. So where we source it, Sometimes we have to source it where the customers want it. For example, a lot of times the United States military will want domestically sourced titanium, what's known as DFAR titanium. And Japan is basically, the military, as far as I know, they're going to be, basically saying that Japanese titanium is DFAR now because we're not smelting any titanium anymore to speak of. How will titanium react with carbon fiber? That's a good one. So what's happening is in America, the workers are not educated well on using titanium. So for example, in the Bremerton shipyard, which is one of our customers, they've been working hard trying to get the workers to adopt using titanium. But of course, the workers are steeped in the manufacturing methods and the techniques with steel and stainless steel. And so before I talk about the carbon fiber thing, I wanted to just point out something here. Now, we are all about sharing what we've learned, flat out. So while some CEOs would sit here and they would not give away secrets, I am like, we need to be moving forward as a culture. We need to be moving forward as a human race into sustainable materials. I'm a big believer in that. The reason why people have a hard time working with titanium is because they don't understand that titanium does not conduct heat well. It's almost an insulator. So when you're drilling a piece of titanium with a drill bit, the heat at the cutting zone skyrockets and does not get distributed into the rest of the material like a heat sink. And so it starts sparking and it tears the bit up. The work hardening is also an issue as well, but it's primarily the heat. So the key to machining titanium, cutting titanium, and everything all revolves around the removal of the heat. Another thing about titanium is that titanium is an element, and it's extremely reactive with oxygen. In other words, it wants to bind to oxygen and become stable. It basically turns into titanium dioxide. So if you have a piece of titanium that is extremely hot and you pour water on it, which a lot of people will do because they want to cool stuff down with water, right? When I say hot, I mean, white hot. When you pour water on it, the titanium atoms will suck away
Oh, you got your new toy.
from the water molecule, leaving behind hydrogen, and that will result in an explosion. Some of you may have worked on some of these, big fires that have been at some of these waste scrap yards. But so the problem is you can't use water to cool it down. Now, there's a lot of companies machining titanium using water-based coolants, which we are like totally against that, right? So you just have to realize that in terms of working with it, you've got to keep it cool. You can't use water to cool it. So that means you're going to have to use other coolants that do not have an affinity for titanium. Now, one of the things that happens in terms of the customers is, and the customers are broken into, I think I might have a slide on this, but the customers are broken into two separate groups. The first group is customers who have been working with titanium for decades, know all about it, and in many cases know a lot more about titanium than we do. Rocket engineers, engine designers for aerospace, so on and so forth. These guys know titanium in and out, well-established properties, they got it down. The other group is people who are working with titanium because they have to work with titanium. They don't have a choice. Whatever they're doing, they've discovered that the only material that's going to work for them is titanium. Carbon fiber is one of those. So here's the typical call we will get. Customer calls up, they want to buy some fasteners, say flathead screws, and they need them right now. Turns out the reason why they need them right now is because they're a carbon fiber manufacturer and they've built all these parts, put them into service, who knows where, it could be airplanes, helicopters, whatever. And what's happened is they're getting terrible galvanic corrosion between the stainless steel fasteners and the carbon fiber. The stainless steel fasteners are just literally vaporizing practically. And so they do their investigation, their customer, of course, is irate and so on and so forth. So they realize, oh my God, we needed to be working with titanium because carbon fiber and titanium are basically at the top of the galvanic scale together. And so those who work with carbon fiber that know what they're doing almost universally will use titanium to hold things together. Whereas some of the newer people working in carbon fiber, they're learning the hard way. So this is a huge driver of our business. Unfortunately, these guys that are coming to us and want stuff made, quickly, they're thinking that it's going to be on the shelf, and we're not a distributor or manufacturer. So obviously it takes time to make it. They get upset, so on and so forth. Currently today, we're manufacturing in China, Thailand, Taiwan, and America in Washington State. So have you established standard for titanium is another question. Okay, so we have standards for our own products, our design products. We're AS9100D certified, if you know what that is. And we're AS9100D certified for the manufacture of titanium and for the design of titanium products. As far as we know, we're the only people in North America that have the design aspect of the AS9100D. So have we been working with the standards organization to come up with standards? The answer is no, we have not. More questions?
There's one there from James. Is titanium gauged for size in the same manner as steel, and is titanium magnetic?
Okay, so titanium is not magnetic, it's non-magnetic. So we're building parts for Northwestern University, and they're making a gigantic magnetic shield. And the parts that we're making, they have to be grade 2 titanium because vanadium is slightly magnetic. And so the little bit of vanadium in the grade 5 titanium is a no-go. So if you want to know, say, truly, is grade 5 titanium magnetic? The answer is it's a little bit magnetic, but it's such a small amount, it's not an issue. So grade 2 titanium, pure titanium, is not magnetic at all. And what was the first part of that question? It was a 2-part question, right?
Yes, it was. Is titanium gauged for size in the same manner as steel?
Is it gauged in the same manner as steel? No, it is not. Most titanium being manufactured in the world is being manufactured under the metric system. So it's done by millimeters.
Okay. Catherine has asked, how does titanium compare with Monol?
Okay, so Monol was one of the materials in remechanics we looked at going to. We had originally were hoping we could use Monol instead of stainless steel. Monol is significantly heavier, and so I think I'm gonna let me see if I can pull up a PDF. Just give me just a second here. I should be able to get this because it'll be enlightening. Can you guys see this? Can you see it clear enough to read it?
Just about, yeah.
Let's see if I can't blow it up a little bit, make it bigger. No, that's the wrong one.
It's okay. It's readable.
Readable. Okay. So here's copper nickel, right? And this first column is the yield strength. And then you got elongation, ultimate strength, and the weight, right? So let's just take grade 2 titanium. Now, as you can see, this first group of titanium, these are all unalloyed titanium. And look at the property differences here for unalloyed titanium. You would think that this is friggin' impossible. Look at this. It ranges with a yield strength between 70,000 clear down to 20,000 PSI, but it's unalloyed. How could you have that kind of property differences in an unalloyed material? It's bizarre. Here's grade 5 titanium. This is basically the workhorse. Now, truthfully, there are much better alloys today than grade 5. But because grade 5 has such traction in the marketplace, this is what most of the mills will make grade 5 titanium. So it has a yield strength of 128,000 psi or 880 MPa, right? Now let's go look at Monol. Okay. Monol has a yield strength of 23,900 psi. It has much better elongation, depending on what you're doing, and has an ultimate strength of 55,800 psi. World of difference. Look at the weight over here. Titanium, pounds per cubic inch, is 0.16 pounds per cubic inch. Monol, 0.320 pounds. 0.322 actually. So completely different material. Next question. The Chinese, I want to say something about this. The Chinese are way ahead of everybody else on alloying. These guys, they're not releasing the alloying that they're doing. I mean, all kinds of stuff. We get plates for us to test because it's very hard for them to get guns and that. So they'll send over plates to us for us to do ballistic tests with. And they're producing, of course, they won't tell us what the alloy is, but they're incredible. They're lightweight and they stop bullets. So they're way ahead of us. Now, but most of the titanium the mills produce in China are grade 5 titanium and grade 2 titanium still, but they're making all kinds of other alloys too. Look at some of these other alloys here. Just to, for example, like this beta C alloy, right? 206,000 psi yield strength. Look at the ultimate strength, 218, very close. Elongation at break, 8%. This stuff is rigid. It's really rigid. Yes, this question here is is class such as ABS, DNV, ATC, etc. on board with procedures? Basically, the catamaran that Jim Betts is building got fast-tracked by the Coast Guard. And they got, I believe they got fast-tracked by the Coast Guard because the United States military is pushing really, really hard for American manufacturers and boat yards to start building ships out of titanium. They had to build a section of the hull for the catamaran and then put it through load tests and all this. But the normal bureaucracy that was experienced with, they just shoved it aside and they pushed it through really, really fast. So instead of taking years and years and years to get certification for commercial tourist boat use, they fast-tracked it as fast as possible. I don't know what else to say. That's being driven primarily by the United States military wanting to move forward with titanium as fast as possible. Something you can do is if you go into a Google and you search on Navy titanium ships, all these articles will come up where the Navy's done dog and pony shows all over the place trying to get workers and shipyards to start building stuff out of titanium. Alloyed with what? Okay, so this is from Catherine. When you say alloyed with what, are you talking about the unalloyed or are you talking about the alloyed? For the property differences? Is this what you're?
Whilst we're waiting for that, alloyed. Okay,
so if you look here, let's just take grade 5. So grade 5 is 6% aluminum, 4% vanadium with the balance titanium. Now this strength of metal sheet is on our website. And if you click on this link, it's going to pull up MatWeb. I would imagine most of you guys are familiar with MatWeb. Now let me see, to share this. What do I got to do? I guess I got to stop the share. stop this share. Let me pull this up if I can. Try it again. Can you see this?
Sure can. Yeah.
Okay, so this is MatWeb, and it's going to give all the properties. So a lot of the questions you would have, you can just go in here and type in the titanium and then the grade number, grade 5 or TI6AL4V, and it'll give you everything about this material. And when it comes time for the component elements, so you can see here that by definition, grade 5 has to have 5.5% to 6.75% aluminum by weight. Okay, and vanadium, it must be 3.5% to 4.5%. That's a huge range in alloying with regard to titanium. Varying these numbers here, it's a massive range, results in huge changes in property. So when we're ordering our titanium, of course, we're always getting the material, mechanical and chemical specs for it, because we're going to look at these specs and go, okay, what is this stuff really? Increasing the vanadium results in a higher yield strength, so on and so forth. Now, these in alloying, you're looking at aluminum here, and we're looking at vanadium, but these other elements, carbon, hydrogen, iron, so on and so forth, they have dramatic impact on the properties of the titanium. And so this is why you see for the grade 2, grade 4, grade 3, these unalloyed grades have these huge property swings. And these property swings are caused by these minuscule elements being present in it. So when I say, for example, that iron, that the Soviet Union's, or Russia now, has a little bit higher iron content than normal. So if I was going to order grade 5 came out of Russia or Ukraine, I would expect it to be at the top of the range. It's going to be probably right on the edge with regard to iron contamination. The iron is going to reduce the ductility, and it's going to make it, I don't want to use the word brittle, but it's going to reduce the elongation, okay? Sometimes that iron in there is good. So if we were to go look at the unalloyed titanium, such as grade 4, you're going to see a higher iron content. Now, one of the reasons is why you would want that is because you want to reduce galling. Titanium has a really problem with galling. So sometimes, you know, particularly with the CP titaniums, which are the unalloyed titaniums, commercially pure titaniums, you want a little bit of iron in there to try to arrest the galling properties when you're building things. There's another thing that I want to talk about, and that is bearing surfaces. So titanium is a terrible bearing material, and here's why. I got to digress here just for a minute. If I grab a piece of titanium, okay, and I'm going to stop this share. You guys can see me again, right?
We can. Yeah.
Okay. So here's a titanium bolt that we manufacture here in Washington State, right? When I grab this bolt, I am not touching titanium. It is impossible for me to touch a titanium. I'm touching titanium dioxide, TiO2. What happens is, when we're manufacturing this bolt, when we machine it, within seconds of the machining process, titanium dioxide forms on the surface of the titanium. It is so thin that it's invisible. But as the days go by, that titanium dioxide coating, if you will, it's not really a coating, it's a film, it increases in thickness. And it keeps increasing in thickness until it pretty much arrests itself. In other words, it can't grow any thicker. The reason it can't grow any thicker is because the oxygen cannot penetrate the film to get to the non-reacted titanium. Now, this seems to defy belief, because when I look at this thing, it's shiny, right? Let's see, I mean, it's shiny as could be. You would say, well, titanium dioxide is white. Why is this not getting a white film to it? Why isn't it getting a white hue? It's not getting a white hue because the titanium dioxide is so thin that you can't see it. Light passes right through it. But Oxygen will not pass through it. That's why it doesn't corrode. So the truth of the matter, of course, really is it does corrode. It corrodes very, very fast. But the film that gets built up on the surface of the titanium arrests further corrosion and stops crevice corrosion, of course, in its tracks. Okay. Now, here's an interesting thing, though. Hydrogen, of course, is a smaller atom than an oxygen atom. Hydrogen can penetrate titanium dioxide, especially at elevated temperatures. Okay. So, in reality, I'm not touching titanium, I'm touching titanium dioxide. Titanium dioxide is extremely stable, and that's what's biocompatible. When we're taking parts, human body parts from titanium and putting it in the body, what's really happening is the bone is adhering to the titanium dioxide. The bone is never coming in contact with actual titanium. It's adhering to the titanium dioxide and fusing and literally integrating. One of the problems that we have in our factories is if you get a titanium sliver in your finger, your body will not reject that titanium. Now think about the ramifications of this. A worker gets a piece of titanium in their finger, and depending upon the shape of that sliver will start working its way through their body. And the body will not detect it as a foreign invader. It will detect that titanium dioxide coated sliver as being compatible with the human body, and it will try to incorporate it. So now, of course, I did not know this in the beginning, and now I've got little minute slivers in my fingers. And when I put my hand like that, I can feel them poking inside my body. So, moral of the story is, get a titanium sliver, get it out right away. Do not let it get in there, because it's not going to fester and the body's not going to reject it.
A couple more questions there, Chris. When will we build a titanium submarine?
Some people say that they already have black ops projects and we have titanium submarines. I don't know if it's true or not. I've had some military guys that supposedly know tell me that we do have these awesome titanium submarines. Other people say no way. But I want to go back to this question about shafts and bearings, right? Okay, so we got titanium dioxide on this titanium bolt, right? That coating is what's protecting this titanium. That coating is pretty hard. It's a lot harder than titanium. When we go to machine this, we have to cut below that coating to be able to cut it. Now, let's suppose, and I'll give you a real world example. One of the riggers that's worked with us since 2007, he, the more he learned about titanium, he wanted to build all kinds of stuff. Of course, he's got these little racing sailboats and so on and so forth. So he wanted to have titanium rudder bearings and so forth and so on. So we built them for them. He put them into service, and they wore so fast, it was completely a stun. We could not believe how quickly these pintles and gudgeons got elongated. Reason why is because as soon as the friction going back and forth rubbed off the titanium dioxide coating, then the titanium dioxide coating formed again, and that rubbed off again, and then again and again, and it just erodes away. So titanium does not make a good bearing material. Now that said, you can do things in the manufacturing of titanium to change the properties of the surface of the titanium. I'm not going to get into that now, but it's possible to basically, it's not case hardening, but it's kind of like case hardening. And so what happens is you end up with an extremely tough surface. We've trademarked it. And for example, this particular bolt has what we call a tough type surface on it. And so it's really, really, really hard. You can't scratch it with a pocket knife, a good quality pocket knife. You can take and you can scratch the dimple here, no problem. But if you try to scratch the flats on this thing, it won't scratch out. So there are ways to process it. But in a nutshell, suffice to say, we use bronze. So if we're going to make sheaths and things like this, we're going to make them out of titanium, and then we're going to press in bronze sleeves for the bearing material. Bronze on titanium is a great wear surface because the bronze isn't hard enough to scrub away the titanium dioxide, and so it makes a great bearing mating. material.
There's a couple more questions there. Can you see them, Chris?
Yeah, I'm trying to understand this one. As a boat builder, how would titanium hull affect the shaft and bearing insulation, mostly the water bearing? Well, the shafts are going to be made out of titanium, right? The prop shafts will be made out of titanium. And the bearings are going to be the well, the bearings are not going to be made out of titanium, so they're going to be made out of another material. And that, but whatever material they're going to make it out of, it has to be considerably softer than the titanium dioxide, the hardness of titanium dioxide. Are you also making hose clamps? We have tried to make hose clamps over and over and over, and we're making T-bolt clamps and some other styles of clamps, but the worm drive clamps, we have not been able to crack this. So there are companies making hose clamps. They don't have the same strength as the 316 AWA clamp. I guess AWA isn't making it anymore, but that style of clamp, they don't have the strength that they do. So we do make hose clamps, but they are not your traditional style of hose clamp that you would think where it has a worm drive. Can titanium be heat treated? The answer is yes. I don't know what else to say about that. I can go back and if you go to our website and look at the strength of metals documents in the technical section of our website, you can see that these, the STA stands for solution treated and aged. So, you know, we heat treat stuff when we manufacture stuff. Sometimes we'll heat treat bar and then we'll manufacture the parts from the bar after they've been heat treated. When you buy titanium bar, almost universally, it's annealed. So these numbers that you're seeing where you got 128,000 as the minimum yield strength for grade 5 titanium, that's annealed strength. That's the softest they can get it. Okay, what else?
I think you might have exhausted it, Chris.
Yeah, I know. I went really fast. I know. I didn't.
Right, so you've had people very engaged with you, so it's an interesting topic, isn't it?
Yeah, it's fascinating. The more you learn about titanium, the more you realize you don't know.
Yes, well, I think every day is a school day, as they say, in certainly in the marine surveying world. So, what about sea growth, Kurt?
That's a good one. So what we did is we took titanium and we stuck plates in seawater, hung them off a dock, and left them there for years. It's biocompatible, right? So it shouldn't be biocompatible with sea growth. So sea growth loves it. One of the benefits, for example, this catamaran that they're making, it's going to be awesome because it's not going to require any bottom paint because they're going to be able to scrub it. I think they probably will put bottom paint on it, but the reality is that in terms of pollution and using bottom paint, and because the titanium is hard and has that titanium dioxide coating, like a lot of times if you have a fiberglass boat, you don't want your diver going down there and scraping the living crap out of your boat, digging at it with a chisel. But with titanium, they can go down and they can scrape it, no problem, scrape the barnacles off. So the barnacles do come off easily, but in terms of preventing growth, no, it doesn't prevent growth. It's biocompatible with life. So.
Okay.
I tried to stay on time. 5 minutes left.
Yeah, no, you've done really well time-wise. Any last points before we let Chris move on? No, I think that's it, Chris. So look, thank you very much on behalf of James, Randy, myself. Much appreciated, and thanks for coming along to share your knowledge. I think we're all a bit wiser, so much. And we'll make sure we've got a copy of the video here, so we'll send it around to all the guys as well.
Okay, cool. Okay, I got another appointment I got to do, so I got to go.
Yeah, nice to see you. All the best.
Okay, bye.
Bye-bye. Okay.